Hello guys, good morning to everyone and my name is Mohammed Sabir and today I am here with you. In this sessions we are going to discuss about we take some problem on a first law of thermodynamics and for the open system and closed system. We will solve the numericals and also try to understand how these numericals what you understand what you can learn from these numericals, how you use this calculation procedure to solve the practical problems. Okay, and we will do some numericals on these sessions. The first we will take a numericals this is a gate PYQ numericals. The first problem is what, we have this is a steam turbiner receives steam steady at a 10 bar. The initial pressure of the steam is 10 bar. Okay, and enthalpy is what, this is the enthalpy is what, H1 is what, this is the kilojoule per kg. And discharge at what, this is a discharge at what, P, you can say, this is a 1 bar, P2 is a 1 bar, okay, and S2 is what, H2 is a kilojoule per kg. The work output is this is the work output W, 250 kilojoule per kg. The chances in kinetic and potential energy are negligible. The heat transfer from the casing to the surrounding is what? Basically, we have to find the steam turbine receives steady state at 10 bar and with enthalpy at this, discharge at 1 bar, enthalpy at this, the work output is this, the changes in kinetic and potential negligible. Basically what this is the problem of a steady flow energy equations. Okay, we have a turbiner, the working fluid enters at this pressure and enthalpy is this, and when it exits from the turbiner having pressure is this and enthalpy is this, how much work we get through this turbiner, that is work is what, 250 kilojoule per Kelvin. Now we have to find the what is the heat transfer, how much heat is transferred through the casings. It is basically a steady flow energy equations. The first we write the steady flow energy equations as of E. It is what, this is a Q, this is the left hand side part, we basically supply this much of heat, enthalpy is this will H1 enthalpy plus V1 square by 2G, this is the plus GH1. Okay, this is the potential head, and work is what, this is the work plus H2 plus V2 square by 2G and GH2. Here these all terms are in the specific form. We are basically find the energy heat transfer for the per kg of the working fluid. Okay, now we know, you know about the basically you know about the this much of enthalpy is this. Okay, this is the H1, you put the S2 at here. Okay, you put the H1 S2 at here, and you also can find that this is the work. Okay, you put the work at here because these all terms become zero due to in the question it is given that these terms all are negligible. Okay, so basically we know this and this, easily you can find the Q. Okay, this is a simple question. I think The answer is given is what in a simple procedure for that. This is a good question because for turbine design, like we always try to find the how much heat is transferred through the casing. 2.5 is okay. It's a good question because here the negative heat transfer is what? Like heat is like heat transfer takes place, like heat loss by casing. What is the heat loss by casing? Now we always try to minimize the heat loss. For analysis phase, we basically try to find out the how much heat is generated. Now we overcome what is the methods to overcome this heat transfer. We will do that type of things because the numerical only numerical solving is not important. How you can, like, whether you can interpret these numerical values to the practical problem, this is important. Can you relate these practical results, numerical results, with a practical theories? Like, we find that this much of heat loss is occurring. Okay, so now we try to analyze that, if how we overcome this heat transfer, how we reduce this heat transfer. That is the main questions. You have to think on that, how this heat loss occurs. Okay, this is the main another thinking behind solving the numerical. Now we come to the another numerical, that is what? Now we come to another numerical, that is what? We have a nitrogen gas. We have a nitrogen gas is enclosed in a cylinder by piston. This is piston cylinder problem. This is nitrogen gas. Nitrogen gas is enclosed in a cylinder by piston at an initial condition of 2 bar. Temperature is what? 298 Kelvin, and volume is what? 1 meter cube. In a particular process, this process is what? The PV is equal to constant process, isothermal process. Okay, it is given that until the volume reaches to what? Volume reaches to what? 2 meter cube. It is an expansion, isothermic expansion. The heat exchange from the work interaction for the nitrogen gas is what? We find the work done and we find the entropy delta as universe. Okay, this is a good question. Like, what basically happens in these questions? What basically happened in this question? Basically, the nitrogen gas is filled in this vessel, and basically we provide some heat to the system by using an external element like heater. Whether it is, we have a particular system, like this is the, we maintain the initial pressure, temperature and volume of this cylinder is this. We expand this cylinder up to this volume, 2 meter cube, and we follow this process, isothermal process. Now we find the work done on this process. Like, to easily you can first PV constant V1 given, easily you find the P2. You can find the P2. You know the how you find the work done. Work done is what? Is a PdV. And for what? MRT for the isothermal process, you can write this mRT upon V into dV, because pressure PV multiplication of PV is constant. So ln V2 by V1. Now this is given, this is given, this is given, this is given. How you find this M? What is the mass of this system? Like how much nitrogen is there? Easily you can find this. The PV is equal to mRT. PV is equal to mRT. Because pressure is given, volume is given, M easily you can find, R is given, T is given. So easily you can find the how much work is done by a system to the surrounding. Okay, because this is the expansion process. Now we have also one question, that is delta S for the universe. Enthalpy change, total enthalpy change, entropy change in a universe is what? For this process is should be 0, because the reason is what? Like this is a reversible process. Okay, because isothermal process, when isothermal process becomes feasible, if the process is reversible, the only in a it is only one case when we can say, it is only one case when we can say the isothermal process is feasible. For what? If the process is reversible. If the process is not reversible, we cannot do the isothermal process, because like basically we expand the gas. Simultaneously we have to maintain the constant temperature. This is not possible when the process is suddenly, like the piston suddenly move upward in direction. Okay, this is the main thing. I think you understand what actually I am saying. Now we come to the another problem, that is what? Now we come to another problem, that is what? Like we have a football was inflated to the gauge pressure of this and ambient was this. When the game started with day, the temperature of the stadium is this. This is a good question. Like we have this football. Having a pressure 1 bar and temperature gauge pressure. It is what? The gauge pressure. So easily you can find the P1 is equal to P gauge upon P ATM. Okay, and temperature is what? Temperature is 15 degree Celsius. Okay, and the game started next day. The temperature for next day, the temperature becomes 5 degrees Celsius and the volume is constant. This is what? Centimeter cube. The amount of heat lost by the air in the football and gauge pressure of the air in the football at a, like this is what? This is a volume constant process. For volume constant process, you can apply a PV is equal to mRT. Constant volume, for constant volume V constant, you can write as P1 P2 is equal to T1 T2. You know the P1 T1 T2. Easily you can find that what is the P2. Okay, so you can find this. Now we come to the how you find the heat loss. Heat loss is what is a del Q. Del Q here is a du plus PdV, because this is a constant volume process, but there is no work done. Okay, so it should be 0, and now we remain it remains a one term, that is what? Du. How you can write du is mCv del T. mcv del T. Now the first we have to find the mass of this system. Mass of this system. By using PV is equal to MRT, you can find the mass of the system. Okay. CV, it is given in the question, I think. Because for air, well known, it is well known. The gauge pressure of the air to the must be originally inflated, it would be equivalent to 1 bar at a stadium is. The gauge pressure air to which the ball must have been originally inflated, so that it would be. Okay, it's also a easy questions, you can solve it manually yourself. Now we come to the another question. Now we come to another question, that is what a gas expand in a frictionless piston cylinder arrangement. The expansion process is very slow. Resistance by this and this. This is a good question. Like maximum work utilized. Like basically, it's the concept. Like the main concept it is used in this question. Like we try to understand this. Like this is a piston. This is a piston cylinder arrangement. Okay. Like this. How the gas expand. Like if we provide some external disturbance, then the gas expand and the gas do the work to the surrounding. Like here for the reversible process, basically this is a P atom and this is a P gas. This is a P atom, this is a P gas. For the reversible process, these two pressure must be equal because it moves slowly. In every step, these two pressure must be equal. It may be slight variations due to the slight delta P, like this is a P and this is a minus delta P. Due to the slight pressure variations, it contracts and expand. Okay. This is the main property of the reversible process. Now, in this case, this is an irreversible process, and it is asking that what is the maximum work can be utilized through this particular conditions. That is what is a P gas minus P atom into del V. This is the maximum work utilizations. Okay, you can find this. This is also a good question. Now we come to the. We have also one question, that is like what is given in these questions. Like we have a particularly, like this is like we have this air supply. Okay, initially, like what is given in the question? What is given in the question? Basically, a rigid insulated tank is. This is a rigid you can say, and insulated is what? There is no heat transfer takes place through this wall. Okay, and evacuated. Matlab, it means initial mass is 0. Okay. And what is the quotient demand? The quotient demand is what? The tank is connected with a supply line. The passes 1 megapascal. Okay, this is a supply line of this is a 1 mega of Pascal and 350 degrees Celsius. Okay, and wall connected with the supply line is opened and the tank is charged here until the final pressure in the tank increases. Okay, it's a good question. Like the kind of thing, first we understand the problem. First we understand the problem. What is the demand of the problem? This is problem like unsteady flow equations. How you use the unsteady flow to solve this thermodynamic problem? Like we understand the concept because we will say 2 and 3 questions we will solve in this class, but first we complete this question, then we look. Okay, this is a question is based on the unsteady flow. The first we try to understand the unsteady flow energy equations. Okay, like we have this system. This is a control volume system. This is control volume system. The air enters through here and exit through this outlet. This is a inlet and this is a outlet. Okay. And here like basically this is a heat transfer Q. Like we get this W work from this control volume. This is what like basically the internal energy of this system. U1 M1. This is internal energy of this particular system at a t is equal to 0 plus Hi plus Vi square by 2g plus GH1 is equal to what? Like we supply a del Q heat to the system is it must be equal to what? U2 M2 plus H exit and V square by 2g plus like this is the mass flow rate of Mi and multiply with exit. Okay, this is a work done, this much of work we get. Okay, like how you apply this equations in this particular problem. The first we know that what is a U1, like in initially the system and the control volume is evacuated, like there is no mass, so this term becomes 0 and this term becomes 0 and initially enthalpy is H1 Hi into Mi. Okay, because the air enters with this temperature, so the enthalpy should be equivalent to this temperature. Okay, Hi into Mi. There is no velocity because velocity is negligible. There is no del Q because system is insulated. These all terms become 0. This also be 0. This also be 0. Okay, what is U2 M2? U2 M2 here because there is no exit. So U2 M2 is here. There is no exit flow, so these all term become 0, and work, there is no work interaction, so we can say W becomes 0. So finally we get this equation, that is HI Mi is equal to U2 M2. HI is what? This is a CPTI. CPTI. Okay. Mi, how you relate the Mi into M2? This must be equal, because whatever air whatever air is supplied to this tank must be equivalent to this M2, because initially the system has no mass. Okay, so cancel out, and U2, how you can write that U2? CV T2. CP by CV Ti is equal to T2. By using these expressions, you can find the value of T2. Okay, this is a good question. By using this question, you can understand how you solve the unsteady flow energy equations problems. Okay, because like when we deal a practical system, these equations can be used. Okay, like the differential form of this equation is also available. How you use this differential form? Like this is a simple energy consumption equations. You try the control volume, like how much air is transferred through this inlet, and how much air exit through the outlet. You understand the basic concept and fundamentals, you can solve this problem. This is also a good question, also a good problem. This is also a good problem. Like we have another problem, that is what? This is also a good problem. Like this is a simple problem. This is not so much difficult. Like we have this turbiner. We have this turbiner having a 2 and 1. Okay. H1, V1, Z1, P1, H2, V2, Z2 and P2. It is given that. Okay. What I have to find? Basically, like in these questions, we have to find that specific work of the pump, because the Rankine cycle. Like what is the Rankine cycle? In a Rankine cycle, this is the TS plot of this Rankine cycle. This is a TS down. Okay. Okay, this is a TS down. This is a work done of what? This is a turbiner. Okay, this is a turbiner. We have to find this work, because here this is a boiler process. This is a condenser. This is a turbiner, and this is a pump. We have to find this pump, specific work of this pump. It is a simple formula how to find the specific of this pump. V del P. V del P. Okay. V del P. So in this case, P2 minus P1. Easily you can write like the P1 is the 3 megapascal. P2 is what? 70 megapascal. So you can let that the pressure increases. So this much of pressure we have to maintain. Okay. So easily you can find that 70 minus 3. How you can write this V 1 upon rho in delta P. This is the specific work of the pump. Okay. Like now we come to the another problem. Now we come to another problem. That is what the temperature and pressure of the air in large reservoir are this and this. Okay, this is the problem of nozzle. This is the problem of nozzle. The temperature and pressure of the air in a large reservoir are 400 Kelvin and 3 bar respectively. A converting diverging nozzle exit. We basically we will give a hint. So you can solve by using a simple mathematical, like it's contains mathematical equations. Okay. Like we will cover these numerical next class. Okay, thank you, all the best. We'll meet again, because in these sessions what basically we are doing, like we have solved the problem on the first law of thermodynamics and for the closed system and open system. The basically the thing is what you understand that what actually I'm solving these numerical on the board. The thing is that like when you feel the approach for this problem, like we have to find the heat transfer heat loss for the turbine casing. Like what is the basic approach for that? Like first we uh, it it is to be given that these terms, like initial temperature, pressure must be known. Okay, like we also as an engineer we should know that, like to find this someone, to find the heat loss, what actually we need the equivalent parameters, you can say what parameters we need to find this final CTQ and output. Okay, this is the kind of like engineering applications we will try to understand in your next sessions. Thank you, all the best.